In this video, we're going to review Euler's formula. This expression right here is known as Euler's formula. It's a rather interesting one and has a really quite wide application in complex variable analysis, and in dealing with, and where we're going to be using it is in dealing with the sinusoidal steady state and a concept or a tool known as phasors. So in this video, we're just going to derive it. If you haven't seen it before, you'll get a feel for where it's coming from, and if you have seen it before, this is just a refresher. Look closely at it first of all. It's a fascinating little formula. You've got e, which is the base of the natural logarithm. So e, which is approximately equal to 2.718, that crazy irrational number, raised to the jx power, where j is equal to the square root of -1. So you have this irrational number raised to an imaginary exponent. And it then is equal to the cosine of x plus j sine of x. Where does that come from? Well, we're going to be using Taylor series expansions to derive this. And so I've written down three different Taylor series expansions that we're going to be using. The first of them is the expansion for the function e to the x. And that's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Just as an aside, we can get a little bit better feel or a greater appreciation for the veracity of this expansion by looking at e to the first power, or letting x equal 1. E to the 1 is, of course, e, which the expansion says would be 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. In just the first 5 or 6 terms, it's already approached the letter or the value of e to 2 or 3 decimal places. So hopefully that gives us a comfort level that this is in fact a legitimate expansion, or a legitimate expression for e to the x. The other two common Taylor series expansions that we see are for the sine and cosine. In the sine expansion, you've got x to the first power, minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. Three things to observe. First of all, x is raised only to odd powers in this expansion. That, by the way, is one of the reasons that the sine function is referred to as an odd function. Another point to observe is that the signs alternate. We have a positive sign, negative, and so on. And then the denominator is simply factorials of the odd powers. So 3 factorial, 5 factorial. Now direct your attention to the cosine expansion. Here we have 1 minus x squared over 2 plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. You'll notice that up here we had the odd powers of x, and here we have the even powers of x, beginning with x to the 0th power. Once again, the signs are alternating. Now, keeping this in mind, let's look at letting x equal jx. In other words, let's expand e to the jx. When we do so, we have 1 plus j times x plus j times x squared over 2 factorial plus j times x cubed over 3 factorial, and so on. Notice in the numerator here, in addition to x being squared, cubed to the fourth and fifth, and so on, j is also j to the first, j squared, j cubed, and so on. Let's take a closer look at what happens as we raise j to ever-increasing integer powers. Well, j to the 0th is 1. J to the first power, of course, is just j, and again, j is equal to the square root of -1. J squared would be the square root of -1 squared, or -1. J cubed, we can rewrite that as j squared times j. We just saw that j squared was -1 times j would be -j. Almost to the end. J to the fourth is then j squared times j squared, which is -1 times -1, or +1. One more step will reveal the pattern here. J to the fifth is equal to j to the fourth, which is just 1, times j. Or j to the fifth is just j and gets us back to where we started. In other words, j to the nth power is periodic, and it repeats every 4 terms. So, looking at this, we have plus 1 plus j, minus 1 minus j, plus 1 plus j, minus 1 minus j. With that in mind, take each of these j terms. Here I've got j squared. That gives me a minus 1 here. J cubed is minus j. J to the fourth is a plus 1. J to the fifth is j. Notice, if we take these terms, half of them are real, and half of them still have the imaginary component j in them. If we combine the real terms, we're left with 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. The signs are alternating even powers of x. Here we have j, factoring the j out of all these terms, we're left with j times x to the first power minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. When you look at these two infinite sums, you see that this term right here is just the Taylor series expansion for the cosine of x. This term right here is just the Taylor series expansion for the sine of x. And in fact, we can then say, and have thus proved, that e to the jx is equal to the cosine of x plus j sine of x. Again, we're going to use that as we derive and develop this concept known as phasors that we'll be using as we analyze circuits in the sinusoidal steady state.